Let's look at a hint for textbook problem 40. It says find the eigenvectors of this matrix A, 2, 0, 0, 2. Okay, so looking at this, we can see that it's already in Jordan form. And eigenvectors are, or the eigenvalues, I'm sorry, is 2 twice. Okay, so it has multiplicity of 2, and when we look at the rank, call it R or whatever the rank of A minus lambda I, we get rank of 2, 0, 0, 2 minus 2, 0, 0, 2. So we get the rank of a 0 matrix, so that rank is 0. And so when we're calculating our Q, we see that M minus R is 2 minus 0 is 2. So we need 2 eigenvectors. Now let's look at the method of the textbook, page 257, 258, method number 2 is probably the clearest one for doing this problem. Okay, for this method we want to look at the matrix adjoint of A minus lambda I, adjoint of 2 minus lambda 0, 0, 2 minus lambda. Okay? And so for the first part of the method, it says to take this, evaluate it at well, the adjoint and the matrix are just the same. So we're going to take our matrix here, 2 minus lambda 0, 0, and evaluate it at the eigenvalue. And we see when we do this, we get the 0 matrix. So the first way of using this method would be to take this matrix, put in lambda equals 0, but we don't get any eigenvectors from doing that. Take a column and insert the eigenvalue, but that doesn't give us anything. And so it's a bit confusing, but what we need to do then is look at, as it discusses on page 258, use derivatives of the adjoint matrix. And so in general we have the formula 1 over multiplicity minus 1 factorial, take derivatives, d by d lambda m sub I minus 1 of this adjoint matrix. And then evaluate it at lambda equals lambda I, the multiple eigenvalue we're talking about. For our case, move that up. For our case, m sub I is 2, and our adjoint matrix is this 2 minus lambda. Lambda is 2 as well. And so for multiplicity of 2, we're just going to take the first derivative. This factorial is 2 minus 1. It's just going to be gone, 1 over 1. And so what we're looking at is the derivative with respect to lambda of the matrix 2 minus lambda 0, 0, 2 minus lambda. Okay, and then we're going to take all that, do the derivative first, and then set lambda equal to lambda I. And when we take the derivative, we see that we get, whoops, the derivative of 2 minus lambda with respect to lambda is just negative 1, because the derivative of 2 goes to 0. So we'll get a matrix like this. And then we can look for vectors in here, linearly independent vectors inside this matrix to use as generalized eigenvectors. Well, the first one we can choose, and we get negative 1, 0. To make it a nice form, we could just make it a positive 1, 0. Okay, remember every scalar times the eigenvector is also an eigenvector. But then we can't use that vector again, putting in a different value of lambda, because it gives us the same value. Or we can't take another derivative, because that will give us 0 for a vector. And so we can look to the next column then for a linearly independent vector, and we have the other one of the set. And again, we can make it a positive 1. And that gives us our 2 generalized eigenvectors. for that problem. And that would be our answer.